Okey-doke. Yeah, so these are some of the formulas. Actually, in past years, I've gone into all of these things and gone through all the mathematics of this, and we're not going to do that today. I just removed all of those slides. They're in the book for anyone who wants to follow them. They're quite there. Here's just a simple diagram. Basically, somehow or other, there's going to be a lasing medium, in this case, hot dense lasing medium, and it needs to be made hot. So it could be an electrical bunch of electrons coming through, ionizing things through. So let's say almost like a fluorescent discharge tube, but a discharge plasma of some kind with an electron driven, or it could be lasers that are delivering light. It has to be lasers, not microwaves, because the wavelength of the microwaves would be so long, and we need a plasma that's relatively small, 100 microns, let's say. And in the end, if it's going to have interesting properties, we want it to radiate into a relatively small angle. Initially, there wasn't much coherence with these sources, but there are now, and we'll get to that. And one of the things that, in order to create these plasmas to shorter wavelengths, which is always a great goal, laser people are always trying to get their lasers to go to shorter and shorter wavelengths, and atomic lasers. That has jumped actually to the free electron lasers, have taken that over and own it, and high harmonics have also play a major role now. But in general, for these laser-produced EUV and X-ray lasers, the wavelength that you can get, the power per unit area of illumination that you need on these things scales as lambda to the 4. That's the math that we're not going to do today. But basically, it's a tough game to get to shorter wavelengths, because if you just want to go from, let's say, a 20 nanometer laser, there's a few that you'll see in a moment at 18.2 and 18.9 nanometers. To go another factor of 2 from there, you need more than an order of magnitude of driving power per unit area. So it's a tough game. So here are the basic processes that one can have. This is just for 2 levels. We'll see in a moment why, for instance, this is good to start with, but in the end, you need a 3 or 4 level system to really work. But just for what the basic processes are, if you have an atom in a lower state, there's only 2 states, a lower state and an upper state. If the atom is in the lower level, absorption of a photon could bring it into the upper level, but the photon energy has to be a near perfect match here. In fact, it needs to be a perfect match, but the energy, the transition energy, usually has some width to it, if for no other reason, because of the lifetime. So that we call absorption. Spontaneous emission is once the atom has its electron in this upper level, one of 2 things can happen. On a certain lifetime, this is not an equilibrium state, it's inverted energy. So it's going to drop down with some lifetime, okay? And that's called spontaneous emission. It's in the atom is in the upper level, but it just spontaneously drops down and throws off a photon. And that photon is the exact same energy as this one, okay? But another process is the atom could be in this upper level, but another photon could come by, has to have just the right energy again. And what it will do is, while this atom is in the upper level, so this has got to come quickly before the lifetime would cause the atom to relax into the lower state. This photon has to come before the lifetime is up, okay? Has to be just the right frequency. But what it will do is it will rattle this atomic system. It'll cause an oscillation of this electron, or now we have to talk quantum mechanically. It will cause an oscillation and the electron, the probability of having the electron in the upper level versus the lower will slowly change over a lifetime, okay, would normally, okay? But what happens is with the stimulated photon, it rattles this electron and it throws off the photon that it would have thrown off anyway, but now stimulated by an incoming photon at just the resonant frequency, and now you've got two. And so this is going to lead us to amplified spontaneous emission, okay? So here are the three processes again: absorption, spontaneous emission, stimulated emission. This is kind of a diagram where you might have, this could be for a regular visible laser. It could be a Ti sapphire. I'm sorry, it could be Ti sapphire. I was going to say it could be a ruby laser rod, okay, where energy is, there's a lot of atoms here that are in different states, probably mostly in the lower state, but somehow or other you put energy in and you activate things and you start driving some of those atoms into the upper state, and then they spontaneously throw off a photon. And the photon could just be like this. It's throwing off a photon which happens to be going along the direction of the rod, maybe not. Maybe it's going out the side, as shown here. It can go, that spontaneous emission can go in any direction, okay? The starting of the laser process, however, is the following. If the photon gets thrown out the side, it's just lost. It's not contributing to the laser. But if it happens to send a photon along the axis, then there can be stimulated emission and stimulated emission again, and there can be an avalanche here where the more you get, the more you stimulate, okay? And so in the direction of this geometry, the geometry assists lasing in one direction and in fact in the other direction. There's nothing special here. Both directions can go, okay? Anything off to the side is just lost. In case you're interested in the homework problems, there's only two, and these things we've been talking about are a part of the first question, okay? Basically, what was this process? And what we're going to come to in a moment. Anyway, this is the start of the lasing process. And once it starts, if there's no mirrors here, the radiation just goes out, okay? And it goes out the other side. So in an EUV laser, there in general are no mirrors on here, okay? And that's for two reasons. One, well, the main reason is you'd have to have a good reflectivity to really be helpful. What multi-layer coatings have been used. The problem is that the hot dense plasma destroys the mirrors. So basically they don't work very well. And you have to push them far enough away so that they don't get scorched. And then they're too far, then the timing isn't right. These plasmas don't last so long. We were saying before, maybe 10 picoseconds or something. So if you look at how long it takes light to go back and forth. So mirrors in general don't work for the EUV, but they do work for the visible, and we'll talk about it. An important part of this absorption, spontaneous emission, stimulated emission is what states are the atoms in here? Are they in the lower state or the upper state? And so this is showing an equilibrium energy distribution where you have the ground level, so-called lower level, and an upper level. So these are two excited states, let's say, and there's a ground level. In equilibrium, the most atoms will be in the ground level, and the next in the lower level, and the highest upper level will have the fewest. So that's an equilibrium distribution, named here as a Boltzmann distribution. But in general, if you're near equilibrium, you're not going to have many atoms. You're going to have less atoms in the upper levels and more in the lower levels. So this is an important part. You need to have these three processes, but you need to know about your distribution. And in order to get a laser, you need more in the upper level than the lower level, because here, for instance, this is what you need. So you need a non-equilibrium, inverted energy distribution. So you have the possibility of having more atoms going from the upper level to the lower level. Here, you would have the possibility of more going from the lower, being absorbed, an absorption process, making the atom go from the lower level to the upper level. And there's, okay, so that's not helpful. You want more going this way. And I put the word eureka here because that's a phrase that Charles Towns, who basically is the inventor, as we understand the broader word inventor, of the laser itself, of the process, and for which he and several others got the Nobel Prize. So anyway, this non-equilibrium is absolutely essential. You want to be able to excite this thing, putting energy in a way that you get more atoms in the upper level than the lower level. That's absolutely critical. Okay, so here's an example, however, that's going to bring up why you need a 3-level laser. Maybe you could call this a 4-level. So here's showing a ground level here. I guess it is a 3-level. Here's the ground level, here's the upper level, and here's the lower level. And they're shown off to the side. And what happens is you put in a pump. So it could be a flash lamp surrounding this. Flash of light excites atoms. That's the way the ruby laser works, for instance. Okay, and that gets, so you have some pump of energy. For the EUV lasers, it'll be an electrical discharge where you put an electron beam through here, a discharge, electrical discharge, or for instance, you pump it with laser light, okay? But anyway, in one way or another, you need to take these atoms with a pump and get them into the upper level. So now we're at the upper level, and now you need some spontaneous emission from some other atom nearby to excite this upper level, to excite, to stimulate the atom to go from the upper level to the lower level by this stimulated emission and throw off another photon. So that's the lasing process. The reason why you want the 3rd level is once that's happened, some nice nearby photon of just the right energy comes and excites this transition, stimulates it to get the 2nd photon. Now the atom is in the lower level. So what's going to happen there? If it stays there, it's just perfect for absorption, where it'll bring it back the other way. Okay, and the next photon that comes by would go from the lower level back to the upper level. So you wouldn't have gained anything. You would have thrown off you'd have 2 photons going out, you gained the 1, but soon you'd have an absorption state negating it. So what you need is a very fast decay from the lower level back to the ground state. Okay, so there's the ground state is 1, 2, 3. And so this fast radiative decay, or fast decay of any means, is what's needed. You need to deplete that lower level. So these are the basic parts of lasing in general. I think the next slide is going to show us a visible light laser. No. This is just, yeah. So we tend to talk about an electron dropping from the upper level to the lower level, like it's a little point electron and it drops down in an instant. But quantum mechanics tells us that's not the case. What actually happens is there's a probability of going from the upper level to the lower level. So the probability of being in the upper state drops down. Probability of being in the lower state goes up. Okay, and the characteristic time for that to happen is the lifetime. So you can make some measure of this. Is it 90% or 1 over e squared or something like that? But what's happening is the electron, the atom electron is quantum mechanically the wave function is oscillating between the upper and lower levels with some probability that it's going to go from the upper level to the lower level. Okay, and that's for spontaneous emission. A stimulated emission, you're going to cut this short with a stimulated photon. Okay. Oh yeah. So I mentioned about Charles Townes. So this is a little book where he talks about the process. It's a history, really. It's great reading. As I recall, it's only around 200 pages, and it's an easy read. It's readable if you had a high school physics class. It would be enough to be interesting, you know. If you've had a little bit more than that, it is a really great book. But it's a history, and it's a lot about people and what happened. And I don't know if maybe it'd be interesting to find out who knows about the conflict over the word patent. Who patented the laser? Who, in quote, invented the laser? There was a great patent dispute, and Townes lost it, even though he was the true inventor of it. He lost the patent, and somebody else got really rich at his cost. So I'm just interested. Are any of you aware of that early history of the laser? No, okay. I'm not so surprised. Anyway, this is a great read. It's something you can read in just a few hours. It's an airplane book, but it's by our own Charles Townes, who died last year at the age of 99. And I've probably mentioned a few stories about him. So here's our classical visible light laser and laser cavity. So here's the lasing medium, which could be a ruby rod, for instance. It's cut at Brewster's angle, so there's no reflections going back and forth. There's no reflection at the Brewster angle, as you recall, right? So there's a certain polarization will have no reflection, and all the other polarizations will have some loss, and so one will dominate, and you'll get a certain polarization. So they're shown a flash lamp that's going to flash light that puts energy in here and at a photon energy high enough to excite atoms into an upper state. So that's going to start the process, and then it looks like what we showed you before. Photons initially they go in all directions, and the ones that go out the side, or they don't quite make it into the geometry that's allowed here, they're lost. It's just lost energy in the startup process. But pretty soon that's not going to happen, because after a while, the photons which go along axis one way or the other are going to start to dominate, and they'll be dominant in that all those atoms that were in an upper state and threw out their photon in the wrong direction, they're not going to have a chance to do that, because this avalanche of ever-increasing number of photons going in a certain direction is going to happen in a time shorter than a lifetime, and they're going to scoop up and stimulate these photons to go in a direction set by the geometry. So that will start the directionality of it. And that's also part of that first homework problem. So it was the slides we talked about up to now, plus the initial directionality comes from just the geometry of this thing, how long and what diameter. Eventually it gets affected by a pinhole we're going to put here, but that's how it starts. Okay, so light starts amplifying, going in one direction, let's say starting with this one, and it's going to hit the mirror, come back, get amplified again, hit the mirror, back mirror, come back and forth. So we're going to take this apart and look at it piece by piece. Okay, so here's our amplified spontaneous emission in a long rod. Some photons initially thrown off at the side, okay? And then there's a geometry, there's an angular amplification here just because of geometry. This isn't some special coherence issue. It's just, at least not yet, it's just the geometry, okay? And so the angle, the emission angle, is basically the diameter of the rod over the length, okay? And that's at startup. And everything goes in both directions. So you've got photons coming out to the right and photons coming out to the left, okay? So that may change depending on the cavity and components we put around it, but that's the way it starts. Okay. So now we put mirrors on both sides, okay? And the one mirror will be as close to 100% as we can, and it will be curved to sort of give some focus to the radiation, probably in a region around here where we're going to put the pinhole in a moment, okay? And the other mirror is a flat mirror. You don't want it to be 100% because you want some light to get through to be the laser output, okay? So 98% might be a number that you use. So now you start this early process, the flash lamp goes off, it stimulates, it excites atoms into upper states. They start dropping back, spontaneous emission going all over the place, some going in just the right direction. And those that go in the right direction get this sort of beginning some little fluctuations again. These, okay, is how the process starts. And it gets amplified, goes through, no reflection at Brewster's angle, hits the mirror, a little bit comes through, but most of it, 98%, gets reflected back. And now you're not starting from noise so much anymore. Now you're starting from an incoming, it's starting to build up to be a wave with contributions from many atoms. And it gets a big amplification through here, okay? Hits the back mirror and comes through again. And now with each succeeding round in this early startup, you're getting a significant amplification of this thing, and you're building up. So pulses are coming out by the round trip time, okay, and they're getting ever more intense, okay. And as they become more intense, they'll be taking they'll be driving electrons in the upper state because there's more and more of these of the photons now. It's like an avalanche effect. They'll be causing atoms in their way or in their path that are in the upper state to give up their photon. The stimulated emission happens. And now there are going to be less of those atoms in the excited state that could radiate a photon in some uninteresting direction. Okay, so the process starts. Okay, and what is the line width of this mirror? So this is not spatially coherent light. People think that all lasers are coherent. Not the case. In fact, don't let me go too long without telling you two examples, which is also in the homework problem, of lasers which are not coherent at all. But at any rate, in general, this light has an angle and a diameter set by some geometry. It has nothing to do with d dot theta equals lambda over 2. So this is not necessary. So this is not likely to be spatially coherent, just radiation coming out with some distribution. Okay, the spectral bandwidth, this is set by the upper to lower transition energy and lifetime. The line width would be set by that. Okay, it turns out that with the lasing process, we may narrow this, but it typically starts and may stay that way, set by the transition line width between the upper and lower state. Okay. Okay. So now, with this process going on for some time and reaching a situation where basically all the excited atoms are radiating into the modes that we're interested in a relatively narrow angle, okay? But now we put in what is called in the laser word a transverse mode selector. Another name would be a pinhole. And the size of that pinhole is set by our formula, okay? And therefore, now radiation that goes back and forth can only go back and forth if it satisfies this relationship. So light in this startup process, the wave fronts or radiation that would have, just by the geometry, would not make it through this pinhole, well, they're not going to be amplified. They're not going to come back again. They're just going to hit this thing and be absorbed. So the only light that gets amplified is light that satisfies the condition of this pinhole, okay? And now we're amplifying only the part that's spatially coherent. And this is a big difference of a visible light laser and an EUV laser. Or if you remember the undulator radiation, we had undulator radiation, let's say at the ALS from the synchrotron, but if we put a pinhole there, we could get spatially coherent light. But when we did that, we threw away a lot of light. Here, the pinhole, the mode selector, is only amplifying spatially coherent light. So now you don't have the loss mechanism that we had before because of the pinhole. Now the pinhole is just an aperture, and it's imposing spatial coherence. So once you put this in, all the light that comes out is spatially coherent. So that was also part of the homework. This pinhole is setting the spatial coherence. The transition between the upper and lower level is setting the longitudinal coherence, right? The spectral coherence. Okay, so now we've got our lasing medium, we have our flash lamps, we have mirrors, and we have a pinhole. Additionally, and by the way, the pinhole, when you put the pinhole here, the radiation that comes out, so the near Gaussian light that comes out, we call TEM00, transverse electromagnetic mode 00. So, and the only thing extra that's shown here is a so-called longitudinal mode selector, sometimes called an etalon, which has two surfaces which can reflect light. And depending on the separation between the two, you can narrow the spectral bandwidth sort of by another order of magnitude. So sometimes if you really want a long coherence length, you'll put an etalon in to get you longer coherence length, or just because you want to narrow a bandwidth. So spatial and temporal coherence, these are our formulas, and we've just used them, okay? So we don't need to do that. Okay. So spatial and temporal coherence can be imposed to some degree by the components that you put in the cavity or in the EUV outside the cavity, okay? Okay, but in general, these lasers are not fully coherent. You really have to work at it, okay? So now this is to compare the visible laser light we've just been talking about with a laser, an EUV, or even you might call soft X-ray laser, although there have been some lasers that are truly soft X-ray wavelengths as we would think of soft X-rays, but they're few and far between, and most of them don't operate anymore. This thing set by the etalon, I think that's just a statement that's in the wrong place. But here's our EUV laser, and the similar. Somehow or other, light needs to go, energy needs to go in to pump the atoms into the upper levels, and that's shown here as an infrared laser coming in. So for instance, they might use a neodymium or some other at 1.06 laser focused on some thin foil, which has a coating of some atoms that you want to make lasers, okay? And you do the excitation, and then the beginning process is the same as before, except you don't have the advantage of the mirrors and the pinhole, okay? And there is a bit of a refraction issue because you have a plasma now, and light going back and forth. It's at a very short wavelength, so refraction isn't quite so strong as it was for the visible light, but refraction is still an effect, okay, that needs to be dealt with. So some early lasers were in this region, 4 to 46 nanometers, it says. The first two actually, at the same time, it was a recombination laser with, what is it? Hydrogen light, right, single electrons. A recombination laser, hydrogen light carbon. This was done at Princeton University by Shimon Sekever and his team. And around the same time, the people at Lawrence Livermore were using a collisionally pumped laser scheme, and I'll show you both briefly what they did. Later, the Lawrence Livermore team, and this was around 18 nanometers. These were around 20 nanometers, okay? So definitely EUV. Later, at Lawrence Livermore, they went from neon-like to nickel-like. Nickel-like required less energy for pumping to get to short wavelengths, and they were able to get, they see lasing actually down to much shorter wavelengths, to carbon-like laid. So, and then this was extended by the group at the Rutherford Appleton lab in the UK, where they got these nickel-like states into saturation with using silver, indium, tin, and others, okay? And so that was a sort of one line of activity, lasted for a certain amount. Not much goes on with those anymore, okay? What happened next was that Jorge Roca, a professor at Colorado State, and his team made a true tabletop lasing at 46.9 nanometers. So it's a kind of, this is truly an EUV wavelength. These, by the way, these facilities, for instance, the carbon, the hydrogen-like carbon at Princeton, that was a sort of a big university laser lab, but okay, the Lawrence Livermore ones, these are the size of a football field, and also at the Rutherford Appleton. So these were mostly big facilities. This, when it says tabletop lasing, the one at 46.9 nanometers was truly tabletop. The lasing parts were as sort of a little bit more than a foot in length. So the whole thing was driven by an electrical discharge. The whole thing could sit on your desk, the whole experiment. So it was truly tabletop. Beyond that came other wavelengths made a different way at wavelengths as short as 13.9 nanometers, and we're going to look at a bunch of them, okay? And these were almost, well, all of these had very low degrees of coherence, and that was quite surprising for them. The team was made up not so much of laser people, but of plasma people, laser people who did the irradiation, plasma people, and but not laser people in the sense that they would understand the properties of the radiation. So they didn't quite realize that this was not really, that it was not spatially coherent. And nor did the people at Colorado State, but a quick application of our formula, d dot theta equals lambda over 2, this is the lambda, just reading the publication and seeing what the diameter of the discharge was, and the radiation angle, it was very close to lasing. So Yanwei Liu was doing a related PhD thesis. He went there and he measured the spatial coherence using the two-slit method and showed that it had a high degree of coherence. So it was the first spatially coherent laser, albeit somewhat longer wavelength, okay? Later, this same group used an entirely different wavelength. This was method. This was driven by an electron discharge. They went to laser irradiated thin film, and they got to much shorter wavelengths. Not so good coherence, but later they combined that with a high harmonic, which was spatially coherent. They used the high harmonic to pump it and got good coherence. Does anyone have a question at this point? Or is this a little too early for a question? Okay, so here's the hydrogen-like carbon. Okay, so this is a carbon plasma, and well, this is the hydrogen-like ion. Okay, and so hydrogen-like, it's got a single electron, but it could be from some not hydrogen atom. So the ion, for instance, in the carbon case, you've stripped off 5 electrons, there's 1 left. So the charge on the nucleus is 6, okay? And the energy the transition energy, which, you know, this is the formula for the hydrogen atom, the Bohr atom, and this works just perfectly to a high degree of accuracy. And with carbon here getting a 36, you could get yourself to pretty high wavelengths. So what happens is they remove all of the electrons. They produce a plasma that's stripped basically of all of its electrons, and then maybe one electron, there's a recombination, so they call it a recombination laser. One of the loose electrons in the plasma comes and sort of recombines and sort of drops down these different levels and eventually gets itself into the n=3 state, where it's long enough lived that another photon can come by and give lasing. And this would be the energy it comes out at. And here it is. This is the transition involved. And this is the photon energy, 68 eV, and it lasers at 18.2 nanometers. So this was among the very first lasers at a very short wavelength that produced a Fizerev letter. And in the same issue, the Livermore group produced its stuff, its first results. So this is the geometry of the Princeton laser, the hydrogen-like carbon, is a little complicated, it turns out. Okay, they produce a plasma. It's in a magnetic field coils to keep the plasma confined for long enough to get some lasing. Okay, here are some details. They actually heat it with a CO2 laser at this intensity. The ionization of the last electron, the fifth electron, where you've only got one electron left, is 490 eV. So they need a certain temperature. Black body would tell us it's going to be in the 150 EV range. Okay, and this is a little bit of what the geometry looked like. But what's interesting is when they looked at the spectrum on axis and off axis, they looked at the spectrum of light coming out twice. In the axial direction, there was this really strong line, okay, at the 18.2 nanometers, the transition we talked about in a moment. Whereas if you look in the transverse direction, wasn't there. There was some other lines that were observed, but this one isn't there. It's because it's not amplified. So that's all I was going to say about the Princeton, the early Princeton results. Around the same time, the Lawrence Livermore group was using the big laser fusion laser to do what's described here as double-sided illumination. So they're putting in 450 picosecond pulses of 2 omega light, so green light coming in. The neodymium laser has been frequency doubled, split into 2 parts, and both parts are coming in. And there's a very thin foil here, just on one side, of selenium. Okay, and this light is focused with a cylindrical focus, which is long in one direction and narrow in the other. So it shows here that it's a 1.1 centimeter long in this direction. That's going to be good for the lasing process, but only 200 microns high, because they need to get a hot enough plasma to ionize the selenium into the ionization level that they want. Okay, so they're going to produce here, it says neon-like selenium. So they're going to remove, they're going to be left with just 10 electrons. So they're going to remove 24 electrons. Okay, and see if they can, and see what happens. And this is what happens. They look at different lengths of foil. So they're going to put different foils in here, some very short, getting longer and longer and longer. And what they see with the short foil, they see this hair of all kinds of emission lines from the plasma. But as the thin foil gets longer in the axial direction, 2 lines start popping up. And when they get to almost an inch long foil, the only thing you see is those 2 lines. Okay, so that's one of the measures of lasing, is that you see an exponential increase in the line. In fact, that's what's shown here. Okay, as they increase the target length, the integrated line intensity is going up, and these are the emission lines that were observed for this neon-like selenium. So neon-like selenium, 3p to 3s, these are the wavelengths that you see, okay? Which they rounded off to 20 or 21 nanometers, I forget, okay? And this was led by Dennis Matthews and a team at Lawrence Livermore, and he's since went to Davis. So this is the scheme, okay? There's the incoming green light, half nanosecond long, strips off 24 electrons, leaves 10. This is the ground state configuration. There's still a lot of, though those electrons are still there and they're at high temperature, and some of them have enough energy to excite these ions into these upper levels. And there's a manifold of states available here. And then there's a lasing down to the third levels, first level, second level, third level, okay? And so there's lasing between this level, a 3p to a 3s transition at these wavelengths, 2 wavelengths, and then the fast radiative decay, get the electrons out of this state so there won't be absorption back into this state. That would be the losing game. That's why, again, we need the 3-level system. So, yeah, I don't want to go there yet. So these two achievements, both publishing in the same PhysRev letter in 1985, were really hot news. So newspapers around the world had feature articles that went on for a year or 2 or 3 with what you could do with an X-ray laser and how this was going to work. It also, if you're aware of the term Star Wars, it didn't involve these people who were driving things with lasers in the laboratory, but other people were claiming they could use nuclear weapons to do similar things at even harder X-ray wavelengths, and that led to what was called the Star Wars proposal, which was going to be a nuclear shield surrounding in space that would shoot down any incoming missile. So that was pure fiction. These wavelengths were then extended by going to nickel-like schemes, and this got us then, so it's a similar scheme, but now you nickel-like, these are the ground states, and I just mentioned them to you because that allowed you to get to much shorter wavelengths. For instance, on both sides of the carbon edge, so you might be able to do some interesting biological imaging was the thought. But you notice that it is a beautiful line emission, okay? But you notice you still see the noise background here. So they were able to get to really short wavelengths, but it was driven by a laser the size of a football field, and the power output wasn't that high, and it was far from coherent, okay? And this is the different wavelengths that they were able to produce. So these were really great achievements, both for plasma physics, for lasers, for spectroscopy, but they haven't been continued because they required such a large facility, okay? I'm not going to say much. We know about refractive index in a plasma, but people, in order to get a longer length and therefore more gain, people in the UK at the Rutherford lab started using the refraction with a split target, okay? And so with a delay of a little bit, 60 picoseconds it says here, okay? And so they produced lasing, saturated lasing at 13.99 nanometers in silver. And so that was also a really exciting thing. It was led by Zhangzhe, for those of you who know how to pronounce it, Zhangzhe, who later, after many years of leading the program there, went back to China, where he was the deputy head of the Chinese Academy of Science. Okay. So this is some of the work that was done at the Rutherford lab under Zhang's direction. Okay, so here's the nickel-like silver, and then they went to even shorter wavelengths, and they got into saturation. Okay. So this is just giving you a sort of survey without a lot of explanation of what people did. Now I want to go to the tabletop situation. So I don't have a photograph of it, but this was the scheme of it. This is the lasing wavelength that was observed. It was in neon-like argon. So you're stripping off 18 electrons, and you're left with 10. And you start with a plasma formed by an electrical discharge, and the electrical discharge is strong enough, and it's so strong, the current is so strong that it creates a magnetic field surrounding it, and the magnetic field compresses the plasma. And when it does, the density and temperature both go way up and reach lasing conditions, and out comes radiation at this photon energy. Okay, and so this is showing what happens when you go from a plasma length of 3 centimeters to 6 and to 12. So at the short length, the interesting line just is not standing out in any way, but with a long enough discharge tube, this gets up to really noticeable lasing. And I think the next one, so here's the average power. This is at a certain rep rate. So it's neon-like, argon plus 8, it says. So it's got 10 neon-like. It's got 10, oh yeah, plus 8, right. And it's a 3p to 3s at this wavelength, and it produces an average power, because it's a rep rate, of milliwatts. So this is quite interesting. So this has been adopted by some people in chemistry there and other places, and it's easy to replicate to make these things. And as we learn later, it was spatially coherent, because the compressed diameter and angle matched our condition. So for instance, these are measurements that were made by Yanwei Liu. So we've heard of him before from several papers on multi-layer mirrors, and he's at LCLS now, working on imaging and controlling the illumination of LCLS, the FEL. But anyway, this is part of his PhD thesis, and he was an AST student, okay? And so he went with, and used the Young's double pinhole to produce an interference pattern, and then just played with the separation of the two pinholes. This was all done in a day or a few days, okay? And this is showing the measurement of the coherence as a function of length, okay? And as it got longer and longer, the lasing got better and better, okay? And this is the interference pattern. It's a very high modulation. This is truly a fully coherent laser. Okay. So that was really exciting also. This was a breakthrough in the laser world, especially the short wavelength world, that there was, first of all, it was compact, and second of all, you could get full coherence with it. So that was a big breakthrough. Unfortunately, scaling to shorter wavelengths, as I've mentioned, because there's 1 over lambda to the 4th, actually even a little bit worse than that. And so, and this is where all those lasers come from. One is that you need, without a high temperature, you don't get a laser. So if you want to go to a shorter wavelength, you need a higher temperature. There's a cross-section involved, that's the stimulated emission, and there's a plasma lifetime involved. And so all of those things make it quite difficult to extend this kind of compact laser to shorter EUV wavelengths. So what that team did was they came up with a completely different scheme, where now they're going to they're going to try to get to these shorter wavelengths, particularly down here. Because of EUV lithography, that team was very interested to get to wavelengths near 13.5 nanometers. And so and you'll see in a moment that they did get lasing at these two wavelengths in cadmium and silver. And this is all due to Jorge Roca at Colorado State. And they continue this research nowadays. But anyway, this is the nickel-like states, okay, that they're pursuing. And as had been done at Lawrence Livermore, but on a much smaller scale and with clever additional ideas. This is years later, but a lot of clever ideas about how to do this. Whoops. What's going on here? Yeah, okay, sorry. Yeah, so this is showing, for example, a molybdenum laser, okay, at 18.9. So these are all going to be nickel-like, okay, molybdenum. And this is showing how as the target length increases, the laser output increases. And eventually, when they get up into saturation, so this is exponential here, and then it levels off to a linear increase with more length. This is showing the 18.9 nanometer lasing. And you can see some of the parameters here. Each pulse has about a microjoule, a duration of 5 picoseconds, and it's 100 hertz rep rate, okay? And this is the so-called gain length product. And this is just pictorially showing the data where this is the 1.5 nanometers would be over here, millimeters, excuse me. And here you're starting to see saturation when you get up to like 4, okay? And then, so I'm sorry, I didn't say one thing here. So this is 18.9 nanometers. Boy, I'm having a hard time. And then they want to get to the shorter wavelengths because of the interest in EUV lithography. And there was an NSF center just focused on that idea of getting to short wavelengths and what you could do in different applications. And this is their work, again, Roca at Colorado State, and a lot of his students. They turned out some great students. And so this is lasing at 13.9 nanometers, producing a millijoule, again, in 8 picosecond pulses, okay? And it's nickel-like, so it's a 4D to 4P transition, okay? And so that's at 13.9, and then there's cadmium, and that was in silver, by the way, and the cadmium just on the other side of 13.5 nanometers at 13.2. I don't see it said here, but that's what it is, okay? And also got into saturation. So, and this is a laser, this is a university laser lab. I would say it's a little bit larger than the high harmonic laser labs on our campus, but not gigantically larger, maybe twice as big, okay? And now this is just a summary of what kind of things did they do. Basically, they started marching along the periodic chart, trying to use the same techniques to get to shorter and shorter wavelengths, and also to get saturation wherever they can, okay? Oh yeah, so this is it's a few years old, but beyond this, there are other results that they've had. They've certainly gotten to shorter wavelengths, but not to saturation, okay? So this is pretty much, it's a little bit out of date, but not too out of date, okay? One thing is, these were all largely incoherent. There was no effort to get this, just get them to lase and get them to saturate was the goal. But they were a long shot from being spatially coherent. So, so here's a technique. Oh yeah. So this is the 13.2. So this is the cadmium laser, 8 picosecond pulses. And largely, you could call it partially coherent. There's an inner part of the radiation within some small angle that does reach a condition of coherence, but it's only when you choose a small angle, about a 20th of the full radiation cone, okay? When you do that, though, you can get spatially coherent. So here's just in red a summary. The input energy from the infrared lasers is about a joule, and it gives an output at 13.2 nanometers. It's like a half millijoule of energy. So the joule in and a millijoule out, which is not bad, okay? And that of that 430 nanojoules, about 1 nanojoule is spatially coherent. So if you did your angle and spatial filtering, you'd reduce the energy, unfortunately, to a nanojoule, but you would get high spatial coherence, okay? And the bandwidth, again, set by the transitions, is about 1 part in 10 to the minus 4, which gives a coherence length at this wavelength of about 10 micron. And the photon flux, this 430 nanojoule per pulse out, corresponds to 2.9 times 10 to the 8 photons. And I made that an exponent, and I made that 5 an exponent before I submitted them today, but it didn't happen. Okay, and again, there's a collaboration here between Yanwei Liu and Berkeley and Rokas and his students. So then, what could you do to improve the coherence of this whole thing? So Roka got the idea of supplementing what he was doing up till then. So let me show you what he was doing up till then. There was some thin film with a variable length, and there was an infrared pulse. It was brought in at an angle because of the refraction allowed for a little bit more glancing incidence, gave a longer path of absorption along the full length, okay? So the main pulse driving this thing was this pump pulse coming in from the side. And in order to limit the refraction, okay, and increase the absorption, there's a pre-pulse. So as we've learned with the EUV lithography, these pre-pulses are very important in that both they provide a pre-ionization to get your ions at just about the right level before the pump pulse comes in and you use the pump pulse energy more efficiently, but also it expands the plasma so there's less refraction, okay? So that's what they were doing up to now, and not having much spatial coherence. What Roka got the idea was, why don't I take a high harmonic, which has a high degree of spatial coherence, and choose a geometry here and materials so that the lasing wavelength here and the high harmonic coming in are the same. And so he had a high harmonic that was timed to come into this plasma just as the main pulse was creating the inversion. And now you got the lasing that you got before with a narrow spectrum set by whatever the material was, and a spatial coherence imposed by the seed pulse, if you will. So this seed pulse was basically putting a lot of photons in at just the right wavelength and producing the lasing effect, stimulating the laser process from an input pulse, a so-called seed pulse. So the seed pulse was providing the stimulation and the spatial coherence. The atoms that you were choosing here, the cadmium or the silver, the transition levels there were giving you a narrow bandwidth. So you had both spatial and temporal coherence. And I think that's the last part of that first homework problem. And this is showing then the lasing process as a function of length and the high harmonics that were produced here in this neon gas cell. So this combined a lot of stuff in this university lab and produced some great PhD theses, okay? And they got to saturation with coherence at 18.9 nanometers. So, and this is showing how the spatial coherence looked with the unseeded beam, the degree of coherence without the high harmonic and with the high harmonic. And you could see that they got very high degree of spatial coherence. So again, it's to go further into shorter wavelengths is a bit of an effort. Then we have a few minutes left. Let me stop. Were there some questions? I was just going to show you some photos of the Nobel laureates who were involved in this, which I know I told you about before, but I enjoy the story. So any questions or comments? Okay, so these are the three people who shared the Nobel Prize for the laser, and one was Charles Townes. He did the work when he was a young assistant professor at Columbia University, and it was a student group, and they worked collaboratively with AT&T Bell Labs, which was nearby, and there was a person there, Art Charlow, that he worked with closely. Initially, his work was on microwave amplification, the maser, okay? But the true goal was to get to a light amplification, which they call the optical maser, but laser, later the better name of laser was invoked. But anyway, so he was at Columbia working with people at AT&T Bell Labs, particularly Art Charlow, who we'll hear about in a moment, and I think I've mentioned him to you in the past too. So that was one. He was actually at MIT when he received the Nobel Prize, and shortly thereafter he came to Berkeley, and then he was in Berkeley until last year. And he shared the prize with two Russians, Nikolai Basov and Alexander Prokhorov, who were, Prokhorov was the thesis advisor to Basov, and they all shared the Nobel Prize for work that was more along the lines of the maser than the laser, but everybody understood what was going on. In fact, here's the quotation. I knew all three quite well. Basov went, besides being head of the Lebedev Physical Institute, was also a member of the Presidium of the Supreme Soviet. So that was as high as he went, other than being the chairman. So he was quite the influential person. Prokhorov was the head of the Russian Academy of Sciences. And okay. Charlow was working with Townes from Bell Labs at the time, and they wrote a paper together, Charlow and Townes, on infrared and optical masers. So this was a paper. When this paper came out, there was a stampede, a rush to see who could follow what they said in this paper and make what became known as a laser. And so the race was on, and I've told you stories about, Charlow, and so Charlow at a certain point moved from Bell Labs to Stanford. So he was at Stanford for many, many years. And I knew him well. And I think I told you about the story about him and my little Volkswagen Bug. But who won the race to get the first laser? And it was Ted Mayman, who made the first laser in Ruby at 6943 angstroms, and he was working at the Hughes Research Labs. And so it was May of 1960. So it's sort of less than 2 years later. And that scheme that I showed you about how you'd make a visible laser is modeled on what he did with the Ruby laser, lasing in chromium. Chromium, I said it right. Okay, interesting for some people here in Berkeley, his bachelor's degree was in engineering physics. We have a big engineering physics undergraduate program with 80 students, okay? So anyway, Mayman submitted his paper to PhysRev Letters, and it's one of the famous stories about PhysRev Letters. They rejected his paper. He had just published a paper saying how he was going to do it, and they said, this is just a little bit more than the past paper. So they rejected it, and he wound up publishing in Nature. Not bad also.
Professor?
Yeah.
I know you said Townes didn't get the patent. So who did?
I'm sorry? Who what?
Who did get the patent? If it was.
Oh, yeah. So I I have to be careful about the names here. There was in Towns's group at Columbia, it was all graduate students and a few postdocs, actually, 2 postdocs. And he collaborated with Charlot at Bell Labs. But there was a student who was looking for a thesis advisor and kept coming to Towns to visit Towns in his office about how he could do a PhD thesis in Towns' group. And they were working on the maser, but they wanted to work on the laser. So Towns would tell him in their weekly meetings, which went on for quite a few weeks, how the different things work, why a cavity was needed, what was the role of the mirrors and the stimulated emission and everything else. And this student, one of his names is Gordon, but you have to be careful because there was a graduate student in Towns's lab who was an above board guy and a great scientist. And one of his names is also Gordon. So I'm afraid I'm going to screw things up. But this one student who was not Towns' student, but was basically pumping him for information. After every meeting he had with Towns, he wrote it in his notebook, and he went to a notary public and had it notarized. And he had this whole history of how you would make a visible laser. And he filed for patents on it, which Towns did not. And he didn't, interestingly enough, he and Charlot went to AT&T and said, why don't you publish it? Why don't you patent it? Because this could have a lot of applications, for instance, with communications, which AT&T would think have some interest in. But the lawyers there said, no, we have no idea. We have no interest in such crazy ideas. And they refused to patent it. And so this I don't know what you call him, but anyway, this student who had gotten all his information filed a patent, and the patent office upheld the patents. And so that guy made a lot of money. He lost a lot of friends, but he made a lot of money, and he continued to have a career. And that's all described in this book, how the laser happened rather than how the laser was invented. Okay. Okay, so we talked about those guys. So more recently, we had the Nobel Prize that involved Gerard Moreau and Donna Strickland, who were both at Rochester, the University of Rochester at the time, and they got it for what was called chirp pulse amplification, CPA. So what happens was people had learned how to make short pulses at the time, but when they tried to amplify them, they would destroy the glass or the host of the whatever the laser medium was. They were usually solid state for the high power laser. The short pulses, when they tried to amplify them, they would be so intense, the nonlinear refractive index would cause a focusing of the laser light, and they would destroy the glass. I've seen many of these long laser rods that people had that were just shattered at the end. Okay, so what they got the idea was, let's take that very short pulse, because it's a short pulse, Fourier analysis would say it has a wide spectrum. Let's take it and spread it out spread out all the wavelengths so it's not so intense and it's a longer pulse. In other words, by using the frequency content, they would spread it into a longer pulse and amplify the long pulse, which they could do. And then after the amplification, then they bring all the wavelengths back together into a short pulse. So that's the chirp pulse amplification that they got the Nobel Prize for. They were both at Rochester at the time. Gerard is now at École Polytechnique in Palaiseau, and still at Michigan too. I think he has a joint appointment, but his main role is in Palaiseau, which is just outside of Paris. And Donna is at the University of Waterloo for their method of generating high-intensity, ultra-short optical pulses. So everybody who's making high-power lasers with short pulses uses this CPA method. Okay, and Donna, so I knew the both of them. Gerard and I often tried to collaborate, but we could never invest enough time to make it work. And Donna was a graduate student at the time, and she had great stories. Right after she won the prize, she came and she gave a talk in the colloquium in the physics department, and she gave a really great talk, which is a recorded, physics department records all those things. It's a really, for many reasons, it's an interesting presentation if you want to search it, okay? Yeah, so basically they use this relationship and the fact that short pulses have a wide spectrum, okay? And this is the scheme, one of the schemes of how they did it. This is showing how it's done today with gratings, but I think at the time, Donna used they used a fiber, a long fiber, okay? And the fiber is dispersive. Inside the fiber, the different wavelengths travel at different speeds. So with a long enough fiber, you could spread out the wavelengths and then do the amplification. And one of the things that Donna said in the colloquium in the physics department here in Berkeley was, people asked her, how did you calculate, how did you know so much about the refractive index and dispersion? How did you know how to accurately calculate how many meters of that fiber you should use? Because it was a lot of meters long, I forget how many. And she laughed and she said, I didn't calculate anything. I broke the fiber and I used the longest piece. So, yeah. So this is a picture of them at the time as they looked, okay? And it is a much referenced paper. And then here's some pictures from the Nobel Prize, which I know I told you about. So here's Girard receiving it, and here's Donna Strickland receiving it. And she told us all, actually she told me about how they had to practice, not with the king, this is the king of Sweden, but how they had to practice shaking hands and holding the handoff of this very heavy, this is a piece of gold like this, so this is heavy. So the king is handing over this heavy medallion, and so the two of them had to practice beforehand. This is the method. And then here are some pictures of Donna with the king receiving it, but they go to dinner afterwards, and the king is escorting Donna, and Donna told us during the colloquium, I think, I spoke to her before and after, and I knew her quite well because I told you we had an NSF center, and she served on our advisory and review committee. So we saw her twice a year for quite a few years. But anyway, she said, how was it that she got chosen to be escorted by the king to dinner? And she said, the priority was he escorts someone who wins the physics prize, and two, if there's a woman, he escorts the woman. So she got escorted to have dinner, and she certainly looks quite happy here. And this is an interesting thing. Donna had been president of the, she had this important paper that was published as a graduate student. She continued to publish leading papers, and she was actually president of the Optical Society of America. But in their wisdom at the University of Waterloo, she was still an associate professor when she won the Nobel Prize. So the brainy people there quickly made her a full professor. And so she told me some funny stories about that. Okay. And then here are just two books about laser fundamentals. There's a book, it may even be in the third edition now, by Bill Silfast. And it's a really great laser book. And Bill is a good friend of mine, and he now writes fiction, by the way. And this is by Tony Siegman. It's an older book on lasers, but it's a great book also. The two books are terrific. So that leaves us ending on time. So I guess that was sort of an overview. We didn't go through any math or anything like that, but I hope it gave you some sense of what's available, what people have achieved, and yeah. So, and there's so I made up a brief homework assignment. Defan said that he would he would put it out today. It's just two problems. And the first problem, we went over all, I think today we went over all aspects of the first problem. And the second one had to do with this coherence. How did they get coherence? By using a high harmonic driver, right? So the spatial coherence of the high harmonic is imposed as a seed on the lasing process. And the bandwidth, however, comes from the material that you chose. What's the, in let's say for nickel like silver or something like that, what's the transition energy, of course, but what's the bandwidth? It's very narrow. So that atomic process sets the bandwidth and the coherence length, but the high harmonic is driving the spatial coherence. So those are the two homework problems, all you have to do, if you choose to do them. So next class I'm going to do X-ray optics. So there's reflective optics, which we've already done, but I'll just show a few slides to remind you very briefly. And then we'll look at diffractive optics like zone plates and stuff like that. And that'll be next lecture. And then the lecture after that will be various aspects of imaging. What do people do with imaging right now? And that's briefer this year than in previous years, but several of you are making presentations which have to do with imaging. So I think everything will work out just fine. Oh, and also there's, this is, people in the College of Engineering, as people in the College of Engineering know this, but there's the Student Honor Society, HKN, and they do the survey of evaluations. And they're gonna come, I think next Thursday at the end of the class at 4:30. So I'll disappear at a certain point. And so I don't know if in chemistry, do you do, or in chemistry or chem engineering, do you do these surveys of each class?
Yeah, but somebody just sends us a Google form, basically. So it's like not during class time.
Okay, so with College of Engineering, HKN will come and they'll say, this is the form, make it out right now. And it would be good if you did it. People in general listen, and I in particular listen. So for instance, one year, 3 students who I had a lot of respect for said to me, don't teach this particular chapter again unless, don't teach this particular topic again unless you can have a written version of the chapter first. It was the chapter on coherence, and apparently it was such a mess that nobody could follow it. So I did not teach the following year. I wrote the missing chapter. So I would say it'd be worthwhile if you do those things. Okay, any questions or comments? No. Okay, see you next time. See you Tuesday.